So we will just look into the programmable logic architectures, right? And we will see that, what kind of architectures are there. And later on, we will move on and see what is an LE. Of course, we have seen what is a logical element. And different companies, as you can see here, different companies do call it, in a different way. For example, Xilinx calls them as CLB, and Microsemi calls it as versatiles, and Altera calls it as logic elements, LE. And a group of LEs is called labs, okay, which is logic array block. See, one thing that you all should understand is, this logic design is a very complex thing where, even though we are just dealing with zeros and ones, okay, with the help of MUX, with the help of FPGA, with the help of LUTs, we can actually realize much larger functionalities. These days, as 5G is booming up, most of the operators, the telecom operators, they do not want to change their hardware. When I say hardware, they do not want to buy new chips. They do not want to invest on new infrastructure, but instead, FPGA is becoming a smart choice for them. Okay, so when I say FPGA is a smart choice, the only reason is because it is configurable. So when I say configurable, FPGA can be used, multi-purpose. So it can function, for example, as a counter, or probably it can function as a adder, right? So multiple functionalities. So these operators are, banking on FPGAs, in order to configure and use it accordingly. Fine. So mainly there are two types of logic blocks. One is LUT based, which is nothing but lookup tables. Okay, sometimes it's also called LUT. Okay, LUT based programming logic blocks, and the other one is MUX, right? Okay, so lookup table contains memory cells along with multiplexers. So it's a combination. Whenever you say logic element, it's a combination with MUX and a flip-flop, right? The output for each input combination is stored in memory cells. So exactly whenever you give this kind of combination, let's say, for example, you're giving 0011. So for 0011, it will know exactly what is going to be the function that has to be done. Okay, so as I give you an example, just like the hardware buttons that you have on your kits. Okay, let's say you have a reset button, you have an on and off switch. Okay, so exactly it knows what is to be done when that particular button is pressed. Okay, so you can correlate that to lookup tables. So predefined functionality is there, and whenever that particular combination is given, let's say 0011, okay, it looks up for that information and immediately it executes whatever it is intended to. You can probably recall the phone directory, right? Or probably your dictionary. So you look up for a word, it goes in alphabetical order, right? So you are you're searching for one word. So here, it's direct. If you compare, the dictionary, okay, the physical dictionary with the soft copy dictionary that we all use. Okay, you just search, and then at the back end in the database, right, it keeps searching and it will exactly map you to that word. Let's say you're searching for a word called apple, right? So the meaning of apple comes, and probably the synonyms also comes up. Okay, so that's an example of an LUT. For a two variable function, 4 memory cells and a 2:1 mux is required. Okay, so it's 2 raised to n, right? So you will have 4 memory cells. So if I have n input, then it's going to be 2 raised to n. Okay, and the combination of mux is going to be the same number of inputs, right? Which means 2 raised to n plus is to 1. Okay, so this is one such example. Okay, how it looks. These are your inputs. Okay, these are your SRAM bits. Okay, so this SRAM bits can be either 0 or 1. Okay, and accordingly it is taken. It is taken as 0, 1, 2, and 3. Okay, and your final output. Okay, so this LUT will act like your select lines, right? So here you can have combination of 0, 1, 2, 3. So which means 0, 0, 0, 1, 1, 0, 1, 1. So this can be the combination. So if you can look at a large scale, right? So, this is how it looks. You have your A here. Okay, then you have 0, 1, all interconnected, just like how you can implement, say, 16:1 mux with the help of, 4:1 mux, okay, where you combine and the outputs are taken to the next level. And again, you will need another mux to select between those outputs and the final mux between the previous multiplexers. Okay, so lookup table, whenever we hear the term lookup table, okay, immediately this should come into your mind. It will have a functional generator. Okay, the reason why it's called LUT4 is because it has 4 number of inputs: x1, x2, x3, and x4. Okay, and this will have a function generator. It will have a D flip-flop, and it will have a mux. Okay, and this is going to be the memory, right, where it's going to have 0 or 1. Okay, just like how you saw previously, right, 0 or 1. So this is represented as M. Okay, fine. So each block contains 2 LUT4 and 2 flip-flops. Okay, so we have 2 function generators here and 2 flip-flops, and then obviously we need mux to make selections between multiple inputs. A flip-flop has chip enable, set, and reset inputs. Okay, so either we can set it or we can reset it. You can see S and R here, right? So you can use that option to, it's just like, resetting and setting the values. Maybe you want to set the values to 1 and then you want to reset it. You want to nullify all that was there. You want to clear out the memory, right? So you can use the reset button. So just like that. A mux is used to select in between the combinational and the latched version of LUT output. So you have your LUT here, and then so it will have an option either to select one from the functional generator, or it can just take from the flip-flop. So since this is a D flip-flop, as we know, whatever is the input, the same thing comes across the output side, right? But there's going to be a slight delay. The multiplexer is controlled by a bit stored in the memory, and this is represented as M. Now let us try to implement a function, right, which is a bar b bar c plus a bar b c plus ab using LUT, right? So what is going to happen? As you can see, since we have just ABC here, right, the max that we have is ABC. So we are going to use only 3 input terminals. I'm not going to use the 4th one, right? So x1, x2, x3. Internally, it's x1, x2, x3, but externally, we are calling it as ABC just for our reference. So this is connected. This remains a general diagram. Okay, so which means you need to have functional generator, you need to have flip-flops, you need to have mux, and then the memory, and then the final output through the mux. Okay, fine. So choosing x1 as LSB and x4 as MSB. Okay, x4 input need not to be used, as F1 uses only 3 variables. So as I mentioned, we wouldn't need x4. To store the contents of LUT, the truth table of the function has to be constructed. So as we know, whenever we have this sort of equation, right, we have to construct a truth table. So since this is not in a natural form, right, so I can add AB, then in the small bracket, you can put it as C plus C bar, right? And you can multiply it, okay, and bring it into the standard form, okay, the SOP form. So once you have it in that form, right, you can construct the truth table and you can just implement the LUT. So how do we do it, right? As we saw previously, we can have the final column selected, right? So this is one such idea where we can just have the final column selected. As LUT4 contains 16 memory cells for output, it is better to store the other 8 bits as well, irrespective of X4. So which means we are trying to make use of all the capacity. So what we will do is we have got this data, right? How did we get this data? Through the equation. You can work it out, and you will be able to find out this particular value. So which means F1 is nothing but the function is going to be true if and only if these values. You can probably create a table, okay, having ABC, and then at the last column you can put it as F1, and wherever the value goes true, which means A bar, B bar, C, which means it's going to be 0 0 1. For that, the output is going to turn high. For rest of the values, it's going to be 0. Okay, so that's how you're going to get this. So since we're using 3 inputs here, okay, so I'm going to have 16 memory cells, right? So since I have 16 memory cells, so see here we have 1 2 3 4 5 6 7 8. So I'm going to just duplicate that, right? So I'm just going to duplicate that. Let me just show you. Okay, so whatever that you are seeing till here, yeah, till here is 1, and the rest is just repeated. Okay, so this is again repeated. Fine. So you can see 2 squares here, right? 2 rectangles, where the one in red represents the one which was there previously. Okay, fine. So moving on, next, multiplexer based programmable logic block. So MUX, as I told you, is a very important device where we can select multiple inputs, and we can just pick up one of them and pass it through our output. But LUT requires storage space. Why do you think it needs storage space? As you saw, it has D flip-flop, and this flip-flop is nothing but a storage element. Okay. Fine. So LUT requires storage space to save it, and multiplexers along with basic gates can be used. So either you can use multiplexers or you can use basic gates. The best to use is multiplexers, because you can have multiple inputs and you can just wish to select whichever you want to. So moving on, we can implement the function. The same equation is taken, right, which we had previously. So this is starting from zeros to ones, 4 zeros to 4 ones. Okay, and we can actually put it in terms of C. Okay, the output, we can put it in terms of C. So if in case I have this functionality, okay, let us say whatever was there, okay, so I have brought it up here, and if I want to put this F1 in terms of C, right, it's going to compare with C. 0 0, so it's the same as C, so I'll put it as C. 1 1, okay, next 0 1, C bar, okay, next 1 0, okay, so it's going to be C bar, and then 0 0, okay, 0, and 1 0 is going to be 0, 0 1 is going to be 1, and 1 1 is 1. So if you can recall the implementation table that we learned, right? So that's exactly what we are doing here. Okay, so we are going to have that particular thing here. See here, if you can see, okay, you have 1 1 here as well, right? So I will be putting up 1. Okay, so the same implementation table concept is used here. So we are going to have this D flip-flop, right? MUX with combination, and whatever is here, right? The C, okay, C bar, 0 1. So accordingly we are going to take based on AB's combination. So AB is going to be our select line, 0 0 0 1 1 0 1 1, right? So based on that we are going to get the outputs. So as 3 variables, we can choose 4:1 mux. 1 4:1 mux is sufficient. which has two select lines, so which means 0, 0, 0, 1, 1, 0, 1, 1. The truth table can be constructed so as to have it in terms of C. The mux select lines can be A and B, and the mux input lines can be in terms of C. Okay, fine. So let us say now, I'm going to have 1, 1. Okay, let's say AB is 1, 1. Okay, so since I have it 1 here, I've stored that value here. Okay, and now let us say it is 0, 0. Okay, 0, 0. So it will take me to C. So whatever is C, that will pass through and come as output. Fine. So these are, some of the general things that you will have to know, which company and what are the devices, and what is the general architecture that they use. Are they using SOT or SOM, which is C of modules, C of tiles? Xilinx, they mostly prefer SRAM. Okay, and Microsemi uses flash. One thing you should remember is flash is going to be a little expensive. Okay, and then as as I was mentioning, the number of read-write cycles also will be considered here. We cannot have more number of read-write cycles. And then Atmel also, majority of them, if you can see here, right, they've used the SRAM memory. So in Altera, you have Cyclone, okay, Stratix and Apex and all those stuff, right? So you can just go through this. Fine. So moving on to programmable interconnects, right? So that's one best thing about our configurable logics, right? CLBs, where we can configure things, where we can make sure that how my interconnects are connecting from one point to another, right? So let us see the logical block here, the switch matrix, right? We have seen different kind of architectures, right? So this is one among them. The interconnect in between the logic blocks should provide flexible interconnection between the rows and columns, right? So if I want to take up one logic block from here, and probably I need to connect this logic block here, right? So these two are going to be my worst cases. So how do? I can probably take it from here, get the switch matrix, right? And then I can come to this logic block, okay? And then I can connect it to the final, or probably there's another path, switch matrix, okay? And then I come to the switch matrix and then directly connect my final logic block. So this kind of connections are called cross-point switch matrix, okay? So where you have 4x4 matrix, right? This represents a connection, the green, the dark one, right, represents a connection. Okay, then you can have 6-way connection, okay, just like a rhombus. Okay, this is going to be 1, 2, 3, 4, 5, 6. So this is a 6-way connection, right? So in this way we can reduce the size, okay, but then it's a little complex compared to this cross-point connections. So to reduce the number of multiple connections for a single route, the cross point can be configured as a 6-way switch. So if you want to reduce, okay, the number of interconnections from one logic block to another logic block, then 6-way switch is going to be fine. But then in order to manufacture, in order to construct, okay, it's going to be a little complex. So the other one that you can see here is a direct interconnection. Okay, so this is going to reduce the delay. So here you can see everywhere there is switch matrix, right? So directly you are passing through. Okay, let us see this in bold. Okay, so directly it's connecting. Okay, so to reduce the delay in the switch matrix, many FPGAs provide direct connections between the logic blocks. So which means they don't have to really pass through switch matrix, but then these lines which are there, okay, they will have to pass through them. So this is one such example where you have 4 neighbors, right? So you have here 1, 2, 3, 4. Okay, so they can connect between them, between the 4 neighbors. So this is a special connection, okay, where you can see that each logic block is interconnected to each other, right? So you can see this here, 1, 2, 3, 4, and then if it has to pass through the corners, right? So it passes through this logic block, it takes the help, and then one of the outputs are taken and given here as input to this logic block. So you can see it can accommodate 3, 3, 6, 7, 8. Yeah, so 8 neighbors it can accommodate with the help of this kind of connections. Next, we have something called global interconnect lines, right? So where you just run these lines across, and whichever logic block is there, they just get connected, okay, to whatever lines is needed. So we call them as global interconnect lines. So which means these lines are, for general purpose. So any logic block can connect to them. Okay. So here I've put up a small, waveform where you can understand, the concept of skew, right? So let us say clock 1 was rising from this point, and then it's maintaining that level and then coming down. So we expect, the other clock also, to be, at the same time. So let us see here, this is our input, this is our buffer, okay, and we have a D flip-flop, and then we have another second D flip-flop. So if you can see, it's a single clock, right? It's a single clock, and then it passes through here, so it becomes clock 1. But the same when it passes through buffer and then reaches the second D flip-flop, there is a slight delay. So you should understand, between signals passing through the logical elements, there can be delays. So these logical elements will take up, the clock, okay, and slightly it's going to be delayed. So that is what you can see. Instead of happening at this instant, slightly it's moved forward, and that particular difference between clock 1 and clock 2 can be called as skew. Okay. So when the clock is distributed to a few million gates in the chip, the delay in the wire causes the clock edges to arrive at different times. So here, we're just talking of 2 flip-flops, but then once you can just imagine the latest processor, which has billions and billions of transistors. So you can imagine the clock tree synthesis, you can imagine the static timing analysis. Okay, so which means at that particular instant, whenever you provide input, you should be able to receive it. But practically that's not possible, because there is that's a huge circuit, right? And it has to pass through all those logical elements. So there is going to be a considerable amount of delay, and that is nothing but called as a skew. For high fan-out and low skew clock distribution, FPGAs provide routing that can span the entire width and height of the device. So fan-outs are nothing but the number of branches that comes out. Okay, you can probably imagine the number of outputs that comes out from a particular block. And fan-in is nothing but the number of inputs that comes across the input. Okay, so that's fan-in and fan-out. Right. So interconnections in row-based FPGAs. So we are going to see different types. Okay. So this is example. This is an X, this is Y, and this is Z. So these are just some of the example of connections. And you can see here segmented and non-segmented, 2 types. Okay. So when I say segmented, which means that you can see that these lines are available, right? So it's called non-segmented, and here you do not have any connections here, okay, wherein you just have these connections outside and towards the left hand and the right hand side. So the previous interconnections are applicable to matrix based architecture. So we saw 4x4 cross connections, right? Cross point connections. So that is for matrix based, which has symmetrical arrays. For row based architecture, since it's one dimensional, it has arrays of switches in the routing channel, which is situated between the logic blocks. Okay, so this is one such example. So whenever a question is asked, you can represent these for segmented and non-segmented, right? So when three connections are required, okay, so we have put it up as X, Y, and Z. So they can be done in two ways, okay? So one is segmented, which means full length track, and also it is faster. Next, segmented way, this reduced speed, and it also has less number of resources. So if you want to have less number of resources, you can go with segmented. And if you want the full length, okay, full length track, and you want it to be fast, you can select this non-segmented type of connections, right? So you can see here, right, you have X, okay, and here, you don't have it, wherein, you just have one particular line which just connects, and here there is slightly, the lines are disconnected from these connections. So we can call this as non-segmented. Okay, so now programmable IO blocks, right? So remember we had this M block, right? And then we had flip-flop, and then we saw the mux, right? So you can just remember how, this bits are configured with zeros and ones. And usually we will take the help of a transistor. Okay, so transistor is again associated with the supply resistor. Okay, so it is biased properly. And then whatever data is there, if we want to save it, then I put it into D flip-flop, and the outputs are given to mux. Okay, and this becomes my selections. Okay, either I can take the input. Okay, one of the input can be from D flip-flop, or it can go from here, from the XOR gate. So the IO blocks on modern FPGAs allow the use of pin as true or inverted. So you just have two options there, 0 and 1, direct or latched. So when I say direct, it means whatever input is coming, it takes. When I say latched, okay, it stays on, it holds on to the same value, just like stuck at 1 and stuck at 0. The IO options can be selected by the means of configuration memory cells, right? The M. The inversion is performed using an XOR gate. So as you know, the functionality of an XOR gate, same inputs, 0, different, it's going to be 1. So based on that, I can actually configure the output of XOR gate. The direction of pin is decided using the tri-state buffer. Okay, so tri-state buffer, you can imagine that it has 3 values, right? High, low, and another active. Yeah, so selected as active high or active low, and it uses another memory bit. Okay, so M is memory, right? So it will have 0 and 1. Similarly, the rate of change of output, okay, which is nothing but the slew rate. There we saw clock skew, right? Clock skew. And here, we are talking about the slew rate, which means there is slight degradation in the output. And the pull-up option, so open drain, built-in resistor, right? This is an open drain, built-in resistor, can be configured using memory cells. So these are all configured using memory cells. Wherever you see M, there is nothing but the memory cell, right? And again, the company has the options of SRAM, okay, EEPROM, okay, electrically erasable, then flash, anti-fuse technology. So anything can be taken. So you can see that, it's actually a complex structure, right? Wherein this becomes your clock, this line becomes your SRAM, right? And phase lock loop, it maintains the phase, right? It doesn't allow to deviate. Deviations can change the output values, right? So it's maintained in such a way. Then you have flash memory blocks, you have A to D, whatever analog signals are there gets converted to digital, right? You can remember the staircase type of approximation that happens, right? Successive approximation, SAR. So where you use R and 2R ladder type of resistors, right? Then you have your clock circuitry here, right? IO bank. So it's a complex structure altogether, right? So it has a dedicated memory, dedicated arithmetic units, DSP blocks, okay, where it deals with implementing your FFTs, FIRs. So whatever that you are doing manually, okay, so this will take up and compute it with preciseness, right? Then you have your embedded processors, okay. So these processors are used in embedded systems. Washing machines can be an example these days. It's getting more smart, wherein you can just key in your inputs, and accordingly at that point of time it just takes, okay, the instructions and starts executing. Next is the CAM, content addressable memory, right? So this is a kind of memory where in which the content and not the address is used to search the memory. So that's why it's called content addressable memory. Fine. So applications, I say FPGA's applications are really huge, right? It's not just limited to one or two, as I mentioned in the previous class, and also in the start of this lecture, right? Your rapid prototyping in the fields of 5G. So there are enormous fields, okay, wherein it can be implemented. Final products in medium speeds, then glue logic, okay, hardware accelerators. So usually these hardware accelerators are used for, if let's say, for example, you have connected a you want to play a high-end graphics game, for example, right? So you can connect a GPU, a separate GPU dedicated graphical processing unit, okay, and that is a separate hardware, and you need certain software which can actually help in running that hardware. So those are called hardware accelerators, or you can call them as also coprocessors, because they're helping your processor. Your processor alone cannot compute so many stuff, right? So it needs the help of coprocessor. One such example can be your 8086 and 8087, where 8087 works as your coprocessor, arithmetic coprocessor. Okay, so these are, the practical trade-offs that we're going to see. Area of silicon chip should be minimum. Why do you think so? We need minimum because if we have more, more functionalities to be implemented, we need more space. So, which means I should make my transistors small and make them occupy, less space so that I can include functionalities. Power consumed should be minimum. As soon as you charge your phone, if it's getting discharged in, say, half an hour, I don't think so any of you would purchase it, right? So we need a maximum battery life for usage. So similarly here, the speed of operation should be maximum. It should be able to do things faster, and weight of the product should be optimum, right? It should not be too heavy, right? Cost also minimum, delay also minimum. So the path with longest delay in the circuit is called as critical path. So critical path can also be termed as worst case, right? Worst path. So area and delay of circuit are inversely related, right? So the area required and the delay, right? So they are inversely proportional. Energy and delay are also inversely proportional. And the area time product and energy delay product are the metrics used to qualify the circuit. So any circuit for that matter, you should be able to have, faster operation. Okay, it should occupy less space, power consumption should be less, right? The cost should be minimum, all of this, right? It should qualify for all of this. So then only it is called a better product. Mapping, placement, and routing. Okay, this is also an important one where you map, you place them, okay, wherever you want to place, and then you need to connect between those blocks. So connecting between those blocks is nothing but called routing. Okay, so there are three major steps. These are the three major steps, and you can target CPLD, FPGA, okay, mask programmable gate array, then FPGA ASIC, right? Mapping is a process where we are translating the design into available building blocks in the target technology. So we are, it's just like, you're creating a blueprint, okay, and then you're going to decide where, where what lies, where are the IO pads, okay, where you're going to place the buffers, where you're going to place the clock, where are you going to place the memory, all the stuff, right? In other words, the process of binding technology dependent circuits, okay, of the target technology to the technology independent circuits that are in the design. So you are trying to map things, you are trying to, convert from one form to another, basically into blocks. In case of FPGA, the design has to be mapped into muxes. So which means you have seen, in configurable logic blocks, you have extensive use of mux, D flip-flop, and then you had your function generators, right? So let us say, I had one block here, okay, I have another block here, okay. So how do I connect it? Vertical, okay, it vertically comes, then horizontally goes, and then vertically comes and connects. So these are the rows of standard cells, and then these are specialized, as I told you, IO pads. It can be RAM, multiplier, or high-speed adder. So these are the blocks that I was talking to you about. Placement is the process of taking the defined logic and IO blocks from the technology mapper and assigning them to physical locations to the target implementation. So placement plays a very important role. Let's say, for example, if these two blocks are connected very much, okay, so I should place them close. If I place this block very far, okay, so the line that I have to draw and I have to connect to this block becomes larger. So as you know, every millimeter increase in wire increases the resistance and capacitance, whereby your circuit tends to be more delayed, right? So the outputs that are coming across the circuit will be more delayed. We do not want that to happen, right? So we place the blocks which are highly connected close to each other so that there is less wire running through them. So routing is the process of connecting them, right? So place and route are often done with each other. Then there are two algorithms, right? There are two processes that are followed. One is called simulated annealing and iterative improvement. You just have to know this, okay? You don't have to get into what is exactly simulated annealing and iterative improvement. You just have to know what is place and route, what is placement, what is mapping, what are blocks, how should it be connected, okay? And these are, some of the graphs that are generated with the help of simulated annealing, right? One is across temperature and the other one is across cost. So the temperature, is going high. The cost is also too much. So iterative one seems to be much better, but then there's a drastic drop here, right? As the temperature reduces, okay, the cost also reduces. So which means we need to have those cooling facilities whereby our chips remain cool and they operate well. Okay, so annealing is the process used to toughen the metal. Okay, so this is a process. Usually chemical engineers will be working on this. Okay, you heat it and then cool it. So this keeps on repeating. Okay. In a similar fashion for placement and routing, simulated annealing algorithm takes bigger risk in the beginning by making random modifications for a feasible solution and gradually arrives at an optimal solution. Okay, in the beginning, just like high temperature, risky moves are performed. In the next steps, as temperature is reduced, there will be decrease in probability of occurrence of bad moves. So that is what we saw here, right? As the temperature decreases, okay, the cost is also going to reduce and it's going to perform better. In contrast, the iterative improvement algorithm accepts only better solution in each step. Such algorithms are called greedy algorithms, okay, because it needs more. Okay, what is more? Cost will be more, temperature also will be more. At the end of simulated annealing, the algorithm has to be greedy so as to accept only positive moves. Okay, so you just have to know about simulated annealing, right? You can draw the graph and you can explain what it is. So this is going to be our ASIC design flow. Okay, this is going to be the final slide where you can understand, okay, system level specification, then architectures are going to design, then comes your functional verification. It's just like an equation, y is equal to something. You can either verify it with the help of truth table, you can optimize it with the help of K-map, Quinn-Mikkelsky, try to come up with a proper equation, and then you can implement it. So that becomes your circuit design. Then comes your physical design, physical verification. It sends to the fab. Okay, we send it to the fab, and then we get it manufactured. Okay, then we do a testing. It comes back, and then if it's fine, then we go with mass production. Now again, here physical design has all these steps, right? Partitioning, chip planning, placement, clock tree. In short, this is also called CTS, clock tree synthesis. So where clocking of signals are checked, okay, and then you have signal routing and timing closure. Right? So these are, some of the things that you have to remember with regards to FPGA. Okay. Okay. So these are, the applications. So not just limited to these four, but as I mentioned, it can be, still more. Fine. So these are, some of the design flow for FPGA, the steps that you need to know: creating behavioral RTL or structural model using HDL. So which means, RTL is nothing but your register transfer logic, right? So you're creating a logic where you're trying to model a device and write its characteristics. So you're going to simulate and debug the design. So you want to know as to what code you have written, and you want to simulate and check for errors. Synthesize the design, targeting the desired device. So you will try to synthesize, as we know that synthesis is bringing up the circuitry form, right? That your text-based code is going to get converted, and you're going to have the circuitry form. Then run a mapping of the design that will break the logic diagram into pieces that will fit into CLB. So now we need to, break them into small bits and pieces so that we make sure that it is fitting in some logic block, right? So each configurable logic block will have, as I mentioned, will have a D flip-flop, will have mux, right? So we need to categorize them. Run the place and route program to place the logic blocks in FPGA and to route the interconnection. So usually, this concept is very large. When I say place and route, you would have heard the term PNR, placement and routing, right? Where you place different blocks, okay, and then you make connections between them, okay. So that is nothing but your place and route. Next, run a program that will generate the bit pattern that is necessary to program the FPGA. Now you have seen generate bit file, right? So when we have done our interfacing programs in the laboratories, so we used to select the option generate bit file, right? So once we do that, a bit file gets generated, and then that's where, it gets connected to your device. right? So which means the Spartan kit. Download the bit pattern into the configuration cells and test for the operation of FPGA. So once you transfer the bit file, the next process is what? To check if everything is working fine. So you want to see if it's up counting, if it's down counting, right? All of that. Fine. So, this is just for your understanding. You have your algorithm design, system, test bench, the whatever requirements you have, and then you are passing this to something called hardware design and verification. First is algorithm, the next is design and verification. 70% of the time is spent in testing and verification, right? So all this happens: synthesis, mapping, placement and routing, behavioral simulation, functional simulation, static timing. Remember, we spoke about the clock skew, right? So timing analysis is done, timing simulation, back annotation. We again, get the extracted value. For example, GDS2. You'll be learning more about this GDS2 file once you take up your CMOS laboratories, right? Where I'll be showing exclusively how this back annotation can be done. So here again in algorithm, you have fixed point, timing, architecture. Okay, then here with system bench, you have analog models, digital models. So for any design, right, you need to have some certain models, just like how you create a library, and in that library, you combine, and then you can call it whenever you want. You write a program and then you can call it, right? Just like that. So these are some of the important abbreviations that you will have to know, right? CPLD, FPGA, right? LEC, LUT. So all these abbreviations are important. Right. So now we will move on to designing with FPGA, right? So when I say designing with FPGA, how are we going to use this MUX, and how are we going to use the flip-flops and get things done? So always you should remember your CLB will have a function generator and a D flip-flop. So if I want to select between these outputs, then it means I'm going to use a MUX here. Either I take it from here or here, right? Our next stage is actually a MUX, having a memory as selection line. Each CLB in the FPGA contains 4 variable function generators, okay? 4 variable, 2 LUTs. So that's why it's called LUT4, which means 4 inputs. Okay, let us take this equation as an example. Okay, so this is nothing but your MUX. Okay, so we will try and implement this, and you can see how it's done. Okay, so in order to have this, okay, so I will break this M into 2 sections, right? So first I'll be taking these 2 terms, and then I'll be taking these 2 terms, and then finally I'll be merging them. So that is where you can see M1. Okay, so M1, I'll be taking one of those sections, and then M2, again I will have another section, and then final M is going to have the combination of both M1 and M2. Okay, right. So if I have to implement this, then the same equation, S0 is here. Okay, so since we are seeing, here we do not need the extra input line, which is X4. We just need these 3 input lines, X1, X2, X3, as like we saw previously, right? So we don't have here, I4, right? It's just 0, 1, 2, 3, and then we have S0, S1, S2, S3, right? So we categorize them and we take I0, I1, S0. So you can see here I0, I1, S0. So this goes to first MUX. Next, in the second MUX, okay, you have another select line. You take I2 and I3. Then in the final one, you take the values of M1 and M2. So M1 is taken when it's 0, M2 is taken when it's 1, whenever the select line is 1. And then the final. Okay, so it passes through D flip-flop. Okay, and whatever is the output of this function generator, it's passing through D flip-flop. And then again, I need to have a function generator here. Okay, because I have multiple inputs, right? So multiple inputs are here, and then it's passing through another D flip-flop. Final M is here. Okay. Now, instead of logic equations, modern FPGAs use LUT. So as I was mentioning, LUT is lookup table, right? So you have your set of outputs here, right? How did we get these values? Based on the equation, based on this equation. So 1, 2, 3, 4, you should be having 4 ones. 1, 2, 3, 4, 4 ones for that particular combination. For this particular design of 4:1 mux, the contents of LUT4 are as this. So each LUT can implement 1-bit function of 4 input variables. So again, it's like if I have 4 inputs, then 16 combinations. So for each combination, I need 1 cell, and that cell is made up of SRAM, right? So if I include the don't care term, so here the 3 input bit is going to become 4 input. Okay, so you will need 3 LUT which has 4 inputs. Okay, so they will require around 48 SRAM cells. So these are nothing but the number of combinations. So as the number of SRAMs increase, the cost also increases because we need to keep manufacturing them, right? And it's an expensive process. If the CLB in the FPGA has provision to combine, so we are coming out with some kind of alternative design, right? Where instead we will use mux for this. Okay, so mux is used, and then through mux we route it off. So FPGA has a provision to combine the outputs of function generators. Then mux can be implemented using a single CLB, configurable logic block. Okay, so this was implemented in XC4000 series. So you have your function generator, right? 1, 2, and these are passed here. You just have the mux here, and then final output. This method uses 2 4 LUTs, okay, LUT4s, and 1 LUT3. So here, instead of having another input of LUT, you are just using 3. So whereby, based on the requirement, we are changing the type of LUT. Here we had 4 input, here we have 3 inputs. Similarly, if we have to see for a ring counter, right? So what's a ring counter? Whatever value is there here, T1 passes to Q1, right? And then Q1 passes to D2, D2 passes to Q2, and finally Q4, Q4 is equal to D1. Right, so you can see that D1 is equal to Q4, D2, D3, D4. How will you implement? The same thing, right? You can just imagine this D flip-flop as your function generator, right? So it passes through, it goes through a D flip-flop, and then this gets into another function generator. So you can imagine, okay, between every D flip-flop, there is going to be a function generator, right? So this function generator is here, you can imagine. So this D flip-flop is here. Okay, let me just annotate and show you. Okay, so this D flip-flop is here. Okay, so the value passes, and then it has to pass to the next D flip-flop. So this D flip-flop is here. So before passing to it, it has a function generator. Now after this, it has to pass through another D flip-flop, right? This D flip-flop. So between D flip-flops, I have one function generator. Okay, so that's how it works. Fine. And the final output, right? The Q4 is getting routed to your first function generator. right? Even though the function generators are of no use, they have to be used because that's in the design, right? That's how it is built. Okay, so we have here I0, we have the true value, complemented value of I0, I1, I2, and we have gates D0 to D7. Okay, so how many CLBs are required to implement this 3:8 decoder, right? So if the decoder is implemented using logic gates, we need 3 NOT gates and 8 AND gates are required. So how will you have that? Based on your equation, right? Based on the equation, you will know what is the final number of gates. When CLB is used, as there are 8 outputs from D0 to D7, 1 for each input combination, 8 function generators are required, as each CLB contains 2 sets. So which means I will need 4 function generators, okay, function generator of 4 inputs, and always a flip-flops, because that's the general diagram, right? That's the general structure, how it is. The number of CLBs required is 4. Okay. So I0, I7, 3 select lines, okay, 8:1 mux, then my final output. If LUT based FPGA is used, each output 8 SRAM cells and 8:1 mux is required. So we will need how many LUTs? 8 LUTs, because it's corresponding to each input. So each input we are passing through an function generator. Okay, so from here it gets into D flip-flop, right? So either we can use a function generator or a lookup table. But in the CLB, as the function generator contains 16 SRAM cells, including the don't care, right? So how is it 16? Because we have 4 inputs, right? 4 inputs. So 2 into 2, 4, 4 twos are 8, 8 twos are 16. So we have 16 combinations, and for each combination, we need an SRAM, right? So 16 into 8, because each is what? 8 bits. So SRAM is capable of just 1 bit, 0 or 1. So we need 128 SRAM cells. Okay, so which means it's going to be more costlier. Now, another important concept that we can think of is Shannon's decomposition. So when you hear the term decomposition, it means that it is reducing. Okay, so if we have a complex equation, now I have LUT4. So when I say LUT4, my LUT is having 4 inputs. Now let us say I have here a function of 5 literates. Okay, A, B, C, D, E, F. So 1, 2, 3, 4, 5, 6. Okay, and how do I decompose it? Right, I have to make sure that I am going to use less number of inputs. So this is one way. I take A outside. So A can either be 0 or it can be 1. So when I take it outside, then I make it as A bar and I replace the A with 0. Since bar is there, it's 0. Then B, C, D, E, F continues. Plus A, then 1, comma. So which means it's going to be A bar into, I take this first term as Z0 and the second one as Z1. So what am I doing? I'm just trying to reduce 1 bit, okay? And I'm going to do that with the help of function generator. So 6 variables have been converted to 5 variables, okay? And finally, I will be giving it to a mux, and I can select either Z0 or Z1, right? Okay. So Shannon's expansion theorem helps to decompose a function containing larger number of variables into function containing lesser number of variables. So we are converting this large number of variables into less number. So that is the idea. So instead of a single 6 variable function generator, we will just need 2 5 variable function generators, okay, with half of a third function generators which are used to realize the function. So which means I'm going to reduce the number of inputs. So Shannon's expansion theorem helps in reduction of hardware. So if I reduce the hardware, it means I'm reducing the number of space. right? Which means I can include more number of transistors or probably other functions I can include on the same board, right? So this theorem is helpful in getting the function reduced, right? So let us take another example and we will understand it much better. So consider z is equal to this equation, and by setting a is equal to 0, okay, so once I set a is equal to 0, which means this total thing goes off, right, because a is 0. And here, okay, since it's 0, so this becomes 1, and b, c, d, e, f, okay, f bar, this will be retained, and here there is no a, so it will just come as it is. So similarly, for a is equal to 1, okay, I will have this particular equation. So I will call this as z0 and z1. So again, here I can have 5 LUTs, 5 input LUTs, along with either a 2:1 mux. You can make a selection here, right? Here you can use a selection with the help of mux. If only 4 input LUT is available in the CLB, then the function needs to be decomposed further by using A and B together, right? So instead of me having just only A, then I can take B also. Remember in the previous slide, I showed you how only when A is taken, okay, I replace A with 0 if I'm taking it as A bar, and I'm replacing A with 1 if I'm taking it as A. So similarly, I can take another variable. I can take B also if my availability is just, okay, 4 input LUTs. Okay, so how do we do it? So this is how, you know, AB is taken, the bar, so 0 0, okay, 0 1 1 0 1 1. This can only be the combination. So in total, what I'm going to do, I'm going to call it as y0, y1, y2, y3. So AB bar into, so this whole thing is taken as y0, this whole thing. Okay, so this whole thing will be taken as y0, and again here y2, right, then y3, right, y0, y1, y2, y3. Okay, right. So Shannon's decomposition theorem helps us to reduce the number of inputs. So similarly, you know, if I just have a 4 variable, then I'll be taking them, then again these 4, okay, I'll have to give it to another 4 variable function generator, and then finally get it. So now you must be thinking, how is that, you know, y0 and y1 is connected only to this, and y2 and y3 is connected? You can see the expression here, right? So based on the expression, okay, wherever they are multiplied, let's say, for example, a bar b bar into y0, right? So a bar b bar into y0. So that is taken into consideration. Accordingly, I will have 2 here, and then from these 2 I can use a mux and either take z0, z. Now let us see another example, right? We will see z is equal to this function, and we can substitute a and b is equal to 0. So which means wherever you have a and b, okay, you will get this particular equation. And then when you have 0 1, you'll be getting this 1 0, then you'll have this 1 1, okay, you'll be having this. Why is it only this? Because let us see here, a bar, okay, so this goes off, and then here b bar, this goes off. So here also, right, so we can, you know, try to reduce this particular equation. We can bring it in a standard form, right? See here, we do not have it, so we can bring it in standard form, and then we can try applying this 0 0 0 1 1 0 1 1. Then finally we will get this kind of equation. So you can see, right, there is a full reduction of variables, right? Again, we can implement it using a 4 function variable, right? Okay, So AB is taken the same example, right? And finally we are getting this. So ultimately what are we understanding? What is the max number of LUTs for realizing a 7 variable function? Okay, so if I have an LUT of 5 input, okay, so which means I'm falling short of 2. So if I'm falling short of 2, then I should take A and B outside. Okay, so I can use 4 LUT5s. Okay, so which means 4 LUTs of 5 inputs. Okay, so the total number of LUT5s required is 6 because you need to make selections right at the end. However, the last LUT5 input remains unused and it can be considered as don't care. I will show you that as well. So this becomes your general form, right? So if you have a 7 variable function, which means you need 2 LUT6 plus 1 mux. If you have 6 variable function, then 2 5 LUTs, okay, LUT5s plus 1 mux. Okay, so everywhere you can see you need a mux and then you need 2 LUTs, but this 5 variable will become 4 input LUT. Okay, so this is what it is, right? You have D, E, F, G, right? D, E, F, G, the same thing. You have D, E, F, G in combination, okay, with A and B. So D, E, F, G, and you have, with respect to D, E, F, G, so 4 inputs, LUTs. Again, you have a mux here. You take these 2 outputs, give it to a mux. These 2, give it to a mux. Final, you will have a mux. So here comes a concept called slice, right? So this is important. If muxes are unavailable in CLB, then more LUTs are needed. Xilinx Spartan FPGA provides mux in addition to LUT4. A logic unit in these FPGAs is called a slice. So this particular section, LUTs and a mux, is called a slice. So it will have LUT, mux, and D flip-flop. So this is one slice. So you can see these LUTs, right? LUT and mux is called one slice. So 1, 2, 3, 4. Fine. So the same thing can be, reduced. You can take this equation as an example, and you can take the expanded version of this equation, and you can use Shannon's decomposition theorem, right? And based on the number of LUTs asked, you can implement it. So if a 7 variable is there and then you wanted 5, then you'll be taking 2 variables outside. And if 2 is there, then it means it's only 4 combinations, 0, 0 to 1, 1, right? Okay. So these are going to be, the standard ways of how it's represented: gate arrays, standard cells. So if you have this standard cell, right, you can actually implement it faster, right? Because it's just like, you just have it ready over the counter, you take it and you can start using it. So this is how complex it's going to look. Okay, so you'll be designing this probably in your next semester. You'll be seeing in CMOS labs, right, where you have your PMOS transistors, NMOS transistors, right? This is the layout. Okay, so there's a complex way of designing things. So cell is defined as a pre-designed and pre-characterized circuit element. So a cell contains pre-tested and pre-stored instances of circuit diagram and its symbol. So it's all pre-done and you can just call them and use it. Okay, so next is about synthesis, right? Synthesis, as we know, it can bring it in circuitry form. And this can have connections between gates, registers, counters, and other adders can be used as basic building. Because see, for any functionality you will need only these, right? You will need gates, flip-flops, registers, counters. So with the help of only these, you can make up any circuit and you can try and implement it. So the representation of the design as a logic schematic together with an associated wire list is called netlist. So netlist is the number of gates and the interconnections that happens between them. Okay, so we know how this works, right? The ampersand represents the AND function. Okay, and this pause edge represents for every rising edge of the clock. So one important flow, right, that you'll have to know: HDL model, synthesis, optimization, mapping, placement, and routing. So this is how your flow goes, which is important, right? So we have seen that previously as well. And the final one actually goes to the fab, and then there they will test how it works, and if any glitches, then again they will send it back to us. Okay, we can rework on it, and the finished product also can be checked, so that becomes your prototype. So once you're fine with that, then you go with mass production. Okay, so case statement, I think we all know how it works, right? For 0, 1, 2, 3, case 0, 1, 2, 3. So this is a normal code where you have module name, and then A and B. So input I'm declaring as A, output is going to be B, and always at A. So A is monitored every time. This becomes the sensitivity list. So again, I'll be using case statements. So which means this becomes my kind of behavioral, right? So at case 0, what is happening? 1. So we will see this, right? So when I say case 0, these two are connected. The select lines are connected. So when I say 0, it means 0, 1. Okay, because this 0 and this 0 is also selected. So 0, 1. Then when I say case, when A is equal to 1, then it means I have 1 and 1. So 1, 1 means 3. So accordingly, 0, 0, which means 0. 0, 1, which means 1. Right? So this is how hardware gets generated. We can either write it in this form, or probably we can more simplify it wherever, this 1 here, right? So that becomes A1 bar and A0, right? And B0 also has 3 ones. So that can also be taken in this form. So once you have these equations, it's very easy for you to represent it in the form of gates. Of course, you are not going to do this. This will happen with the help of software. Okay, now there can be a problem where unintentional latch can be created. So previously we saw all the 3 cases, but then here we're only seeing 0, 1, 2. But then there's a third case. So in this kind of scenarios, right, there will be an unintentional latch created. Unintentional latch means always it will hold on to one particular value. I know the value of 0, 0, 1, 2, but for 3 I do not know. So it's going to hold the previous value. It will just retain that. So that becomes a latch. It is holding on to that value. Okay, so when you synthesize, this is how you're going to get. So what's the mistake here? The mistake here is you will have to add all the case. So you'll have to come with case 3 for A. Okay, so how do we eliminate? I put the case 3 and I get all the values. So there's no latch, no need to depend on the previous outputs. Now, how do we have synthesis for if statements, right? So here, if A is equal to 1, fine, then begin, then I'm going to next state 3, then Z is assigned to 1. So there's no flow here, right? There's no flow here. So it's an ambiguous code. Similarly, here you can see, right, A is equal to 1, and then begin, and then the next state is given 3, right? Then the set is assigned 1, else 2. What about the other states? We don't know, right? So this is also an unambiguous code, right? So it's always nice to give, all the values. Now, let us see module name, inputs, okay, outputs, always at A and B. So if A is equal to 1, so if A is given as 1, okay, then your Z, the output, is given to C. So whatever is in C, that comes to Z. Else, okay, if B is equal to 0, then you can see that D is connecting. Okay, 0, then D is connecting, then okay, Z is assigned to D, else the remaining one E is taken. So this becomes a perfect code, and you can actually take here as it is. So 0 0, okay, D E C C, okay, all correlated. So there's no unambiguity here. Similarly, you can do this for arithmetic components, right, where you can generate counters, right? Count is assigned to count plus 1, right? You can generate a 4-bit counters with the help of clock, right? You can take rising edge of the clock. Usually that is taken, right, with the help of assign statements, right? You can just assign them one after the other. So you can see here ACC underscore T is equal to ACC plus B. So B will have a value. B is nothing but your input. Whatever is there for input, okay, that will be adding to your accumulator, right? So counter also can be generated with the help of codes. So logical element, what hardware gets resulted for this type of statement where A is assigned to B. Okay, so when I say A is less than or equal to B, okay, so which means equal to less than, because we have two operators here, right? So either this or this, so I have to use a OR gate. Okay, so if you try to synthesize this, okay, this is what you're going to get with your comparator. So as we all know, less than or equal to is relational operator, and this will come inside the always block. So similarly, now I'm setting the value to 3. Okay, so in that case, okay, 0, A0, A1, okay, this should be 1 and 1, right? So 1 1. So A is equal to 3, 1 1. So this is the LSB and this is the MSB, right? So synthesizer may produce a 4-bit comparator with A and 3 inputs. Okay, for optimizing, we can break it up into each bits. Okay, we can say not of third bit, which is A3, and then not of A2. So we can either break it up like this. This is the hard way. Okay, and this is the easy way of representing. So there are some kind of ideal requirements, okay, or some practical trade-offs that we'll have to consider. So we will see them one by one now.